Hello again, everyone. I'm John Ball, and today I want to take you through the next generation of large language models. What we're pursuing is the original goals of artificial intelligence, which is how to create intelligent machines that are effectively emulating humans, because the only example that we've got of an intelligent machine today is a human being. When people talk about AGIs here tomorrow, the joke is that since the 1940s and 50s, people have been saying that within 5 or 10 years, or maybe within a generation, we'll have intelligent machines. And we're never getting there because there's a difference between hardworking engineers and scientists. The missing piece has been the science. And in my opinion, the science comes from cognitive science, because by simply studying how our brain works and how psychology and philosophy and linguistics works, that gives us enough information to know what it is we're emulating, rather than computer science. This is an example of how linguistics works, and I'm not going to take you through it today because of time. I will run through this, but here we've got John and Beth wanted to try to promise Beth, Sue, and Samantha to eat the hamburgers, a sloppy Joe, and a BLT. Now, when I say that really quickly, you have no trouble following what I'm saying. You probably wouldn't be able to remember it, but that's the type of thing that LLMs need to cope with. So the next generation of LLM is going to be based on this meaning-based technology. That's my expectation. But let's not go into the detail of what the meaning is there. Let's just look at the fact that the final frontier in science is understanding our brain, and it's not about how computers work and applying a computer to our brain. A better model is to look at what our brain does and then emulating it. If I want to recognize a box, I've got 6 examples of a box here, and if I can simply match in my visual field anytime I see one of these boxes and say, hey, there's a box, I could then connect it up and do things with it. So the idea is that we can simply build these templates that would recognize either visual or audio or any type of sensory input, and by storing those patterns that we've learned from experience and then refining them over time, we can recognize things very efficiently. The computational model, for those who haven't seen it, it's typically done with coordinates. So if you had a box and you wanted to replicate it with math, you could simply say, well, I've got a box that's got a length of 2, and if I draw my XYZ coordinates, I'm going to finish up with something that math can generate for me. Okay, well, let's have a look at how patterns work in a combinatorial system. And it's quite different to the computational model, and you'll see the difference in a moment, and you'll see how brains align with this model. So the first thing, if you wanted to learn how to write words in English, you would learn the alphabet. So one of the letters of the alphabet is the letter C, and the letter C has a lot of variations that are still the letter C. You can potentially just map it out as an arc or whatever, but what we want to do is more than just the visual part. We want to connect it to a meaning layer. So the green bit represents the meaning layer, and in this case, we can say C has a category. It's a kind of letter. It's a letter. And we can also identify here, some of them are capital and some of them are lowercase. So we could associate with each one of these elements, not only is it a letter, but we can have some refined categorization, which might just be telling us that it's a capital and nothing else. But that's not enough for language. We need more. And well, there we go. We can simply add some other letters. We can learn the whole alphabet and some digits, and now we've got the ability to recognize the fact that there are letters and so forth in our meaning repository. So obviously the meanings would be extended at this point. But that's the basis for now going to the combinatorial level. So here, in order to recognize the word cat, if you were a computer scientist, you'd say allocate 3 memory units, and then in each one encode the details for C, A, and T in sequence. And there's your representation. But a different way of doing it that deals with the varieties of ways that we can recognize C, A, and T is we can simply allocate 3 units, and we can point. The first one's pointing to C, the second one points to the A, and the last one points to the T. So we can use the visual recognition plus the fact that the sequence matches in order to identify a different meaning. In this case, the fact that it's a word, that's its category, and it means something. And we've got a lot of flexibility on that point. But this isn't enough, is it? Because we're missing something. We're missing what those words sound like. So here, we can identify the sound C, and we can connect it to the fact that it's a letter, the letter C, and cat we can recognize as the way you would hear that word. Obviously, hearing's not enough. We need more, and here we get speech. So speech is traditionally in a different area to these others in our brain. But what it needs to do is control the muscle. So it needs to control my breathing, my vocal cords, my mouth movements, probably other things in order to pronounce the word C. And so there's muscle control, there's hearing, auditory control, and vision. And those are actually in different parts of our brain. This one starts in the occipital lobe for vision and finishes up in our temporal lobe. This is in a different part of our temporal lobe for auditory. And this is in our frontal lobe. And this meaning is located in a different area, like Wernicke's area rather than Broca's area. And the fact that there's these different regions in a brain was input to Patom theory. And as a result, Patom theory comes from the science, not the other way around. Comes from our observations of the science, not the other way around. So there we go. AGI is here. Maybe it's here today. What I've just shown you is that the computational model has been holding back AI because in the early days of AI, there were computer scientists and mathematicians. So if we now pivot from that focus on computers to one based on Patom theory, that's an alternative way to try and solve the problems that have proven to be quite difficult. So, for example, it's always been very difficult to do the animal-like skills of sensory inputs, motor control, balance, touch, those types of things. So we can now take AI to the next level. It's a very exciting time to be around. And in terms of the language applications, I'll be taking you through in the coming weeks the types of things that we can already do in language by using Patom theory with a linguistic framework, role and reference grammar. So thanks very much for joining me today. Look forward to seeing you again soon. Bye for now.